So today what we're going to work on and look at and it's limits involving infinity. So these are going to be limits that as we get closer to a number, they're going to equal infinity. And I'm going to show you graphically using a table and then using number sense. And I showed you all of these last year in Honors Math 3, okay? So if we look at this graph, this is the graph of f of x, which is the graph of 1 over x minus 2. Okay, it's the reciprocal function that's been translated right to, okay? So if I want to find the limit as x approaches 2 of f of x. Okay, I want to know what that equals, right? Well, what I have to do is, again, this is a limit, right? As x approaches 2, I have to do the one-sided limits. I have to take a look at those. So we would take a look at the limit as x approaches 2 from the left of f of x. Okay, so as x approaches 2 from the left, so that'd be on the function to the left of 2 and going towards 2, right? What does the y values do? Well, they shoot down, right? And they're going to negative infinity. So this is equal to negative infinity, okay? We can also take a look at the limit as x approaches 2 from the right of f of x. So that'd be to the right of 2, so that'd be on the function, okay? And we're going to go towards 2. So my point, as x gets closer and closer to 2 from the right, my y's for those points are increasing drastically, right? They're going like straight up. So this is equal to positive infinity, okay? Neither one of these exists, so this one can't exist, okay? So what we would say is we would say this limit does not exist. And we can look at the graph, right, and tell, but we don't always have a graph to look at, okay? It's great if we do, we can read it, right? But what if you don't, okay? So let's look at the table next. All right, so using a table, looking at the same function, we want to approach 2 from, let's do 2 from the right, okay? So if we approach 2 from the right, okay, that would be something like 2.5, and then 2.1, 2.01, 2.001, and even closer would be 2.0001, okay? All right, and when x is 2.5, my y value is 2. When it's 2.1, it's 10. And you could build a table on the calculator like I showed you, okay? When it's 2.01, it's 100. 2.001, it's 1,000. 2.0001, and we get 10,000. Now, what is this table describing? This is describing the limit as x approaches 2 from the right for our function f of x. And as x is getting closer and closer to 2, okay, what are our y's doing? Our function values, they're going towards infinity, right? So that's confirming what we did just right here from the graph, from right above, this one, right? Okay, let's make x go to 2, but from the left side. So that would be something like this, 1.5, 1.9, 1.99, 1.999, and then 1.9999. Usually 4 places is enough, okay? At 1.5, it's -2. At 1.9, it's -10. 1.99, it's -100. At 1.999, it's -1,000. Okay, and at 1.9999, I think I said 4 nines, okay, it'd be -10,000. So this table is describing the limit as x is approaching 2 from the left of f of x. And that's equal to negative infinity because these are getting bigger and bigger and bigger in a negative way. Okay, so how do you do this if you don't have a graph and you can't create a table, okay? What if you just have the function, okay? So f of x is equal to 1 over x minus 2. And here's some ideas, okay? If you take a number and you divide by a really small number, the result, okay, this has to be really small. Okay, so this has to be close, so small it's close to 0. and that's what I mean by a small number, okay? A number that's really close to 0, that winds up being equal to a really big number. Like if you take 5 and divide by 0.001, so let me grab a calculator. Okay, usually I have my students do this with me, okay? So something like this, take the number 5 and divide by 0.0001. That's a number that's really close to 0, right? And if I press enter, I get a big number, right? If I take 7 and divide by 0.000003, that's also a really small number. That's the number that's really close to 0, right? And we get a big number, right? So that's what I'm saying here. And that's going to be the idea behind these, okay? All right. Something that's going to come up in the next few days is this. What if you take a number and divide by a big number? Okay, that's going to equal a small number. So dividing any number by a really big number, you're dividing that number into a lot of parts, right? So it's going to make each part smaller, okay? So when I say small here, again, this is going to result in a number that's close to 0. Okay. So here we go. Okay, how do we figure this out? Okay, how do we figure something like this out? The limit as x approaches 2 from the left of f of x. Okay, so what we want to do is get a number, you know, like 2 decimal places is probably good enough. Okay, that's to the left of 2. Okay, and we're just going to try. Now you got it. You can't put equal here. Please do not put equal. I will mark it wrong. Okay, because it's wrong. This is giving us an idea of the behavior of this. Okay, I should have said this at the very beginning. Anytime only the denominator is 0, that's going to result in a vertical asymptote. And we talked about that last year. Okay, so 0 over 0 is a whole, but a number over 0 is going to be a vertical asymptote. Okay, so for this one, let's pick a number that's to the left of 2, but really close to it, something like this. X is equal to 1.99. Okay, and let's put that in for x and see what the heck do we get out. Okay, so what is f of 1.99? Okay, so this would be something like this, 1 over 1.99 minus 2. Okay, so 1.99 minus 2, okay, that's going to be 1 divided by, and this is going to be a negative number. And you're only 0.01 away, so it's negative 0.01. Okay, this number is really close to 0. So we're dividing by a really small number, which is going to make the output a really big number. But the numerator is positive and the denominator is negative, so this is going to actually come out to be a negative big number. And what negative big number really means is this is equivalent to negative infinity. So this is like a movie, like it keeps going. This is like a picture, like a snapshot. Okay, this is only one. It's not infinity. It's just this is going to be a really negative big number. If you did this, it's going to give you a number. Whereas this is telling you it just keeps going and getting bigger in the negative direction. Okay, so what about this one? How about the limit as x approaches 2 from the right of f of x? Okay, so to do this one, we're going to need to look at this. How about let's go like 1/100th away from this, but to the right. So that would be something like 2.01. I mean, you could go even closer, 2.001. Okay, this is good enough though. Okay, to figure out what's going on. So f of 2.01, that's going to be 1 over 2.01 minus 2. That's going to give me 1 over, once again, this, but it's going to be positive, right? 0.01. So once again, this is a number that's close to 0. And anytime we divide by a number, and this is getting, remember, this x is getting closer and closer and closer to 2. So this is getting closer and closer and closer to being 0. Okay, and so this is going to be a positive big number. And the reason I know it's positive is because we're taking a positive 1 and dividing by a positive 0.01. So it's going to be a positive big number. So that means this one is going to go to infinity. And that's a way to figure this out without a table. Okay, it takes some number sense or some algebra. Okay, all right. Okay, so what is the definition of a vertical asymptote? Well, it actually takes limits. Okay, so you can't say, oh, there's a vertical asymptote here because it makes the denominator 0. No, that's not the definition of what a vertical asymptote is. Okay, and I'll mark it wrong. Okay, because it's incorrect and you're thinking like that. Okay, so the line x equals c is a vertical asymptote of the graph of a function y equals f of x if either. So you're approaching some number c from the left, or you're approaching some number c from the right for your function, and the output to that, okay, that limit is either infinity or negative infinity. So please don't think it's plus or minus infinity. What I'm saying here is it could be either one. So you're approaching some number from the left, and it equals either infinity or negative infinity. Automatically, boom, you have a vertical asymptote there, okay? This one, or it could be both too, because that's what the or means. The limit as x approaches c from the right. So you're approaching some number c from the right for the function, and the result is it's either infinity or it's negative infinity. That's when you know you have a vertical asymptote. It's the only time you know, okay? All right, so some parent functions that have vertical asymptotes, okay? So let me slide this up a little bit. You need to know that definition, by the way, okay? So f of x is equal to 1 over x. That's one we just did, okay? F of x is equal to log of x. So all logarithms will have a vertical asymptote, okay? And we also have to pay attention to the domains of these, okay? So f of x is equal to the natural log of x. Trig functions we got to watch out for. F of x is equal to tan of x. Y, okay? Y tan x, because tan x could be written as sine of x over cosine of x. You're going to see that a lot, okay? And so this denominator could be 0, okay? So f of x is equal to cotangent x. That one, because cotangent x could be written as cosine x over sine of x. Another trig function is f of x is equal to cosecant of x. Why is that one? Because you could have 1 over sine of x. Cosecant x is the same as 1 over sine x. F of x is equal to secant x. Why is that one? Why is that one going to have a vertical asymptote? It's 1 over cosine of x. And so whenever cosine of x is 0, that's going to cause this to have a vertical asymptote. Whenever sine of x is 0, it's going to cause this one to have a vertical asymptote there. Whatever values would that make cosine of x be 0, that's going to make tan x have a vertical asymptote. And the same thing here. These can't be written as fractions, okay? You just have to know these parent functions, okay? So for rational functions, you want to find values of x that make the denominator 0, but not the numerator. Not the numerator. If it makes the numerator 0, that's going to be a whole, okay? And then we want to investigate the behavior with a table or use number sense, okay? For logarithm functions, find the values that make the argument equal to 0. Now, the argument is what you're taking the log of, okay? And then you can investigate the behavior with a table, or you can take a picture, or not take a picture, but picture in your mind what the graph would look like, okay? All right, so let's do this first example. So for this function, 4 over x minus 2 squared, okay, 4 is never going to be 0, so because it's 4. So that's going to be that you can't have a whole. This function will not have a whole. But depending, you could, if the denominator becomes 0 and the numerator is 4, you could have a vertical asymptote, okay? So we would set x minus 2 squared equal to 0. That's going to happen when x is equal to 2, okay? So we have to take a look at two things. We have to take a look at the limit as x approaches 2 from the left for our function. See what that comes out to be. And we also want to take the limit as x approaches 2 from the right of our function. Okay, so To the left of 2, a good number to try would be something like this. X is equal to 1.99. Okay, so that's going to look like this. I'm just going to do a quick calculation down here on the bottom. This would be 4 over 1.99 minus 2 squared. Okay, so that would be 4 over, well, 1.99 minus 2 would be negative 0.1 squared, right? So what's negative 0. You know what? I'm sorry. I just did a calculation error. Okay, so this is going to be right here. This is going to be negative 0.01 squared. Okay, now that's 4. This number is really, really close to being 0, right? It's close to 0, but when we square this negative value, it's going to become positive. So that means that when this happens, when this gets closer and closer to 2, this is going to be a number that's getting closer and closer to 0, but negative. But we're squaring that negative value, which causes this denominator to be positive. So overall, this gets closer and closer to infinity, okay? So this is infinity. Why? Because this is equal to a positive big number. Maybe I should have put positive here. A positive big number, okay? How about if we go just a little bit to the right of 2? So something like this, x is 2.01. That's just to the right. Let's take a look and see what happens when we put these numbers in. So this would be 4 over 2.01 minus 2 squared. That'd be 4 over 0.01 squared. Well, that's a number that's really close to 0, right? When we square, it's going to be even smaller, okay, even closer to 0. Okay, so this is going to be a number that's really, really big, but positive. A really big positive number. That means this one comes out to be infinity, okay? All right, because the definition of vertical asymptote, okay, that if x approaches a number from either the left or the right, and the result is infinity or negative infinity, that tells you there's a vertical asymptote. So you got to know the definition, okay? This means whenever this happens, okay, as x approaches 2 from either the left or the right, or not, it doesn't have to be 2, a number, okay? Then we'd have a vertical asymptote at this x value, okay? So because of these right here, there's a vertical asymptote at x is equal to 2. They test you on the AP exam whether you know and how to justify an argument. So and how to use theorems. Okay, that's one of the standards. Okay, do you know what this means? If you have either one of this, then that automatically means you have a vertical asymptote. Okay, let's go to the next problem. All right, for this next problem, find the vertical asymptote, if any, for f of x is equal to x squared plus 2x minus 8 over x squared minus 4. All right. Okay, so you should notice this is a difference of squares right here. And this might be factorable, right? Okay, so that when we factor it, it's going to help us understand, like, okay, what are the pieces? What's happening here, okay? It won't be the justification of why, okay, there's a vertical asymptote, but there will be, okay? So two numbers that multiply to give you -8 and add to give you 2, that would be 4 and -2. So this factors into x plus 4 times x minus 2. That's how the numerator factors. The denominator is x squared minus 4. That's a difference of squares. So that's x plus 2 times x minus 2. I think I just said that wrong. X plus 2 times x minus 2. Sorry, guys. I'm getting tired already this week. All right. Okay. So this x minus 2 and this x minus 2 cancel, right? They make the 1, right? So what that means, what that's telling us is that there's going to be a hole at x equals 2 because that x equals 2 causes the numerator and the denominator to be 0. Okay. Now, vertical asymptotes only make the denominator be 0. Okay. So we look right here. Okay. We can cancel this out and we can actually use this function, x plus 4 over x plus 2. And it's just a little bit easier to calculate. Okay. All right. So we can tell that x plus 2 is equal to 0, right? So that would mean x is equal to -2. That's what we have to investigate, okay? So drawing a number line to help us picture this, right here would be -2, to the right would be -1, and to the left would be -3, okay? So to investigate this, okay, what's going on, we need to take the limit as x approaches -2 from the left of f of x. And we also want the limit as x approaches -2 from the right of f of x. And we want to take a look and see what do these equal, okay? So what's an x value? That's just to the left of -2. So just to the left of -2 would be something like x is equal to -2.1. The last problem I did 2 decimal places, okay? I'm just gonna do 1 decimal place. It's a little bit easier to do the math in our head, okay? All right, so that would make this -2.1 plus 4, okay? And this bottom one would be -2.1 plus 2, right? I'm just putting it into this one. Okay, so when I do this, you don't have to actually do the calculation, okay? Is this number going to be positive or negative? And it's going to be a positive number, right? It's going to be a number that's positive, and it's not close to 0. It's just a positive number. That's all you got to worry about, okay? This number right here, -2.1 plus 2, is going to wind up being a negative number, but it's also going to be close to 0. Okay, and if that's close to 0 and it's negative, okay, that's going to give us a big number, right? But because the top is positive and the denominator is negative, that's going to give us a negative big number, which tells us up here that this is going to come out to be negative infinity. Hopefully this is helping, okay? So now the next one, I want to be just a little bit to the right of -2. So like -1.9. That's why I did the number line to help us picture it, okay? So something like this, x is equal to -1.9. So that'd be -1.9 plus 4 over -1.9 plus 2. Once again, this is going to be a positive number. Don't worry about the number value. It's just going to be a positive number. And it's not close to 0. This one's going to be a positive number too, because 2 is bigger than the -1.9, right? So this is also a positive number. But this number, right, -1 that's going to be really, really close. Those are close to canceling each other out, right? So that just means this is going to be a number that's close to 0 again. So when you take a number that's really close to 0, right, and you divide by it, that's going to give you a really big number. But because I'm taking a positive divided by a positive, this is going to give me a positive big number, which is telling you up here this one's going to go to infinity. Okay, so do we have the fact where x is approaching a number value from either the left or the right, and the result is an infinity or negative infinity? And the answer is yes. So because of these two statements right here, not because of this, not because of this, but because of this right here, we know we have a vertical asymptote at x is equal to, and what is this x value? It's -2. Okay, that's actually our answer right here. It's because of this. Like, okay, if somebody says, why is there a vertical asymptote? It's because of that. All right, it's because of the behavior as x approaches -2. It's approaching the result, the function value is either approaching infinity or negative infinity, okay? That is the definition of a vertical asymptote. The definition of vertical asymptote is not, whatever x value makes the denominator 0. No, that's wrong. It's wrong, okay? It's this, okay? If you have either one of these, Sometimes you're only going to have one, okay? That's going to cause you to have a vertical asymptote, okay? All right, let's do the next one. When we can, we always want to write these functions as fractions, basically. They're called rational functions, okay? So let's take a look at something like this. F of x is cotangent x, right? But cotangent x could be rewritten as cosine of x over sine of x, okay? So what we need to do is figure out, okay, so what value causes this to be 0? Now, we just did it above, and we figured out where x plus 2 is equal to 0, right? Well, now we need to figure out where is sine of x is equal to 0. And lo and behold, that stuff that we went over like 2 weeks ago, guess what? It's coming back, right? We got to solve this, okay? All right, so here we go. We're going to solve this, okay? And let's go right here. Well, I should say this. This is this ratio. This is an angle. This is a ratio of the y coordinate over the r. So this is y over r. The only way for y over r to be 0 is when y is 0, because r is the radius of a circle of that points going around. It can't be 0, okay? So y is 0. Well, where is y 0? Well, it's happening right here, and it's happening right here. Okay? So what's going to be kind of funny here? Well, let's say here, this would be x would be 1, y would be 0, and r would be equal to 1. Over here, x is -1, y is 0, and again, r is equal to 1, okay? Now, I'm going to list out, here's an example. Okay, I'm not going to, there's an infinite many vertical asymptotes, okay? So I am not, when there's infinitely many vertical asymptotes, I'm not going to make you figure out the limits, okay? All right? Not on those, okay? All right, so here we go. What are these angle values? Well, x could be, it could be, if we're going this way, it could be 0, it could be 0 radians, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. We could just keep going, right? Because it didn't say anything what x could be, right? We could also be going the opposite direction. Well, that'd be negative pi. So we could have 0 plus a pi or minus pi. So that'd be plus or minus pi. We could go all the way to here this way, or we could go this way, right? So that'd be plus or minus 2 pi, plus or minus 3 pi, plus or minus 4 pi, and so on, okay? So we got to figure out a way. How could we write this without writing them all? Because you can't write them all, okay? And so we went over this last year at the end. It was during when we were distance learning, okay? But what it is you notice these are all pi, right? Even this one is 0 pi. We just don't write it because 0 pi is 0, okay? So all of these are plus or minus 0, plus or minus 1, plus or minus 2, plus or minus 3. So they all have pi in common, and it's 1, 2, 3 positive and negatives, right? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, those are called integers, okay? So we could write a formula for this, and it would be x is equal to n pi, okay? And we would say n is an integer. Okay, so what we would say is that there is a vertical asymptote, or asymptotes, plural, at x is equal to n pi, where n is an integer. Okay, now, I just got through stressing, and I know what I said, okay? You just got through saying that you can't just say, oh, whatever makes the denominator 0 is going to be vertical asymptote. Okay, on trig functions, it's okay. And the reason why is because there's infinitely many of these. you can't sit here and do all the limits. You'd be here forever, and then your grandkids would have to take over, okay, or your kids, and then your grandkids, and then your great grandkids. There's just so many, you can't do all the limit statements, okay? So this is just a behavior that we know, okay? And if you think about the cotangent x graph that we did during distance learning last spring, we graphed it, and yeah, it had vertical isotopes, right? Okay, and it had it at 0, at pi, at 2 pi, at 3 pi, at 4 pi, 5 pi, and so on, okay? All right, let's do the next one. All right, so this is kind of similar to the other one, all right? If you take a look at this, okay, this is natural log, that's a logarithm, okay? Any logarithm, all right, takes on this shape. Okay, there's a vertical isotope right here on the y-axis. The y-axis is a vertical isotope, and it looks like this. And some things you need to know is that this side is going to negative infinity as x is getting closer and closer to 0, okay? It's going to negative infinity. This side keeps going right and keeps going up. Now, it goes up really, really slow. Let me slide down. This side goes up, but it's going up really, really slow, okay? That's why it's kind of flat. It's not flat, but kind of, okay? All right, so this is any logarithm, okay? It doesn't matter what base. I'm just gonna call this one, for simplicity, natural log of x, okay? Now, this x minus 5, recall from last year, that's gonna cause it to move to the right 5. So it's this graph, but it's been shifted to the right 5, okay? So one thing, find the vertical isotopes, if any, for this, okay? Any logarithm, I don't care what the logarithm is, whatever this argument, whenever this argument is 0, that's where our vertical isotopes are going to be. Okay, so this is the argument right here, this x minus 5. So whenever this x minus 5 is equal to 0, or if it was like 3x plus 2, it'd be 3x plus 2 equals 0, okay? We would solve that for x, and we get x equals 5. Okay, so this logarithm is going to have a vertical isotope at 5, okay? But why? Okay, so this one we can do a limit because there's only one limit we need to do, okay? So we know that this moved to the right 5, right? Moved to the right 5. So it's going to look something like this. And this is where it helps to know these graphs, okay? This would be the vertical line. X is equal to 5. And it would be, because I know, why do I know the vertical isotope? Because everything got moved to the right 5. Okay, so the graph would look something like this. Gosh darn, I wish I had you in class last year. I mean, in person, okay? I know I had you in class, but this makes so much easier when you do that, okay? All right. So what we need to do, because we know that there's one at x equals 5, we need to do these two limit statements, okay? So the limit as x approaches 5 from the right of f of x. And based on knowing the shape of this graph, as x is approaching 5 from the right, okay, not using number sense, just using knowing the graph and knowing the parent function, this is going to go down, right? So this is going to be equal to negative infinity. Okay, so what about this side? Well, the function doesn't even exist on that side, right? There's no function over here. Okay, it's not part of the domain. So any value that's to the left of 5 doesn't exist. So we have the limit as x approaches 5 from the left of f of x. Well, there's no function over here to approach it, right? There's nothing, right? So what that means is that this limit does not exist. Okay, so there's two functions where there's a part of the x's that you can't even use, and that's an even root function and logarithm functions. And that's why I stressed so much last year with you guys with domain, okay? It was for this. All the stuff I taught you guys last year had to do with this, okay? One thing you could do is just go to the right, okay? And you look at it like this. Okay, let's go to the right. So let's say 5.1. Okay, that'd be this one, right? And this one, it would help to have a calculator, okay? But you take the natural log of 5.1 minus 5, right? Because that's what the function says, to take 5 away. That would give you natural log of 0.1, okay? When you take the log of a really small number, that's going to give you a really big number, okay? When you take the log of a number that's close to 0, that's going to give you a really, really big number, okay? Let's do this one. X is equal to, let's say, 4.9. And watch what happens. We take the natural log of 4.9 minus 5. That would give you the natural log of negative 0.1. And you can't take the log of a negative value, right? So that's why you can't. There's nothing. You try to put this in your calculator, it gives you an error, okay? Where this one will give you a number and it'll be big, okay? Not too terribly big, okay? All right, let's do the next one. Okay, so this next one is f of x is equal to cosecant of 2x. So if f of x is equal to cosecant of 2x, then this is equivalent to 1 over sine of 2x. That's a trig identity, okay? So now, okay, so this denominator could be 0. So sine of 2x, we're going to solve that. Where does that equal 0? Okay, so we can draw a diagram. Okay, remember, again, this ratio is y over r. So the only way for a ratio of y over r to be 0 is if y is 0. So that's only going to happen right here on the positive x-axis and on the negative x-axis. Right there, my x is 1, my y is 0, my r would be 1. Over here, my x would be negative 1, my y would be 0, and my r would be 1. Okay, and so it's all of these angles again, right? So we'd have 2x, not x, but 2x, because that's our argument right here. 2x could equal, okay, and it would be 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. We could keep going around, right? But we could also go around this way. 0, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi, negative 6 pi. So it could be 2x could either equal 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, plus or minus 4 pi. Now, that's not x, right? Okay, so what would our x be? Well, we'd have to take each of these and divide by 2. So this would be x is equal to 0 pi over 2 plus or minus pi over 2 plus or minus 2 pi over 2. I know that reduces. I wouldn't want to do it though. 3 pi over 2 plus or minus 4 pi over 2 and so on, okay? Now, why didn't I reduce it? Because some of these do reduce, okay? It's because you lose the pattern of what's going on. Well, what if you look at all these, what do they all have in common? Okay, they all have a pi, yes. They're all plus or minus, yes. All the denominators are 2. What's changing? It's this number right here, right? 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Next one would be plus or minus 5, plus or minus 6. Those are all integers, right? So we can write this as, okay, x is equal to n pi over 2, where n is an integer. So what does that mean? Those are the x values that cause this denominator to be 0. Okay, and once again, it's a trig function, and there's infinitely many, so don't worry about writing limit statements because there's too many for you to write, okay? All right, so we have vertical asymptotes. At x is equal to n pi over 2, where n is an integer. Okay. All right, so here we go. Any of the trig functions, all right, the trig functions that have vertical asymptotes, you don't have to write limit statements for, okay? You don't have to write limit statements for, okay? Because it's just too hard on you, okay? It's not worth the effort trying to do it, okay? All right? All right, guys, that's it for today.